look at is we're going to look at this thing known as percent ionization, also known as percent dissociation. After that, we're going to talk about how to deal with weak bases. And we're going to find out when it comes to weak bases, they're extremely easy. If you're comfortable with weak acids, weak bases will be a breeze. Percent ionization. This was something we discussed really quickly in the last period. And one of the things that we said is when it comes to the percent ionization, or once again, also referred to sometimes as percent dissociation, we said that basically what it's going to be is an equation that simply looks at the degree of dissociation of the acid. So if you look at the equation, it says, hey, the percent ionization is equal to the initial concentration of the acid. So whatever the initial concentration is, divided into the actual concentration of the hydronium cation. And if we multiply it times 100, then it tells us, once again, the percent dissociation or percent ionization taking place here. Really easy sort of calculation. And once again, if you look at it, just make sure that you're really careful, initial and equilibrium concentrations here. So one of the things that we gotta look at is we gotta look at what this percent ionization means. And if you look at the equation, it's kind of straightforward. It shows us, once again, the degree at which this thing is going to dissociate. And of course, the higher the percent ionization is going to imply that you get more dissociation, which means you got a higher amount of the hydronium cation being produced. And remember, when it comes to these acids, I'm not afraid of you, but I am afraid of this thing right here. That will be the thing that will cause severe burns, that hydronium cation. So as we get these higher percentages, then we got a stronger, in this case, acid. So to give you an example, if they gave you a problem such as this, we have a 1 molar acetic acid, they give us our Ka, and they want us to go in and figure out, in this case, what the percent dissociation happens to be. And then after that, we're gonna take a look at pretty much the exact same problem. The only difference is that here I'm starting off with a 1 molar solution, and this one I got a 0.1 molar solution. Still the same Kas because it's still acetic acid. I just want to kind of show you how the percent ionization is going to be slightly different between the two. We're still going to calculate the same, but there's just something I'm going to show you here. So if we look at it, if I have this sort of problem here, and they wanted me to figure out what percent ionization is going to be, then I'm going to set up my equilibrium like we always do. I'm going to go ahead and set up my ice table that sits right here. And then once again, one of the things that we already said is we said that when it came to equilibriums of weak acids, the concentration that they provide you, so that concentration will always reflect, in this case, the initial concentration of the acid. So that's always the initial concentration. So I'm always going to place it right here. And then of course, I'm going to have 0, 0, minus x, plus x, plus x, and then 1.0 minus x, and x. And then one of the things I can do is I can go in here and ultimately solve, in this case, for x. Because if I get x, I get the H3O concentration divided by the original concentration. I can tell you in this case what the percent ionization is going to be in this case. Or once again, percent dissociation. Now, of course, one of the things you're going to notice in this particular problem is I'm going to save myself some time here. I'm going to write the actual equilibrium expression, which I have sitting right here. Products of reactants. Everybody raise their coefficients. No solids, no liquids. Perfect. Didn't bring the water into this thing. You'll notice that right here, I got x times x, just substituting in, 1.00 minus x. But one of the things you'll notice is over here, I got rid of my minus x. And the reason why I got rid of the minus x is, remember, we had this test. And we said that if we can take the Ka, multiply it by 100, and if my original concentration of the acid is greater, still greater than that, then I can remove the minus x that we have here. And of course, if I get rid of the minus x, which this is going to pass, if I multiply this by 100, I'm not going to get something that's going to be close to the 1 in this case. So it absolutely passes. Even if I look at it, I went in here and did calculate it, I could say, hey, 1.8 times 10 to the negative 5th times 100. Well, that's going to just cause this thing to go to 1.8 times 10 to the negative 3rd. Well, clearly, that is smaller than the original concentration of 1.00 molar. It passes. I get to remove that minus x sitting there. I don't have to go through the quadratic equation anymore. I solve in this case for the x, knowing that the x happens to be the H3O plus concentration. And if we look at it, one of the things I can see is that for this 1 molar solution, so 1.0 molar solution of acetic acid, so I'm just going to go here, HC2H3O2. This is the exact same formula as this right here. They're just trying to show it as that carboxylic acid sitting right here, but a lot of times we'll kind of express it this way right here. When I look at it, I can see that, hey, you know what? The original concentration is going to be divided into the actual concentration of the hydronium. So we got 4.2 times 10 to the negative third M sitting right here. And that's the concentration of H3O plus. And of course, if I multiply it by 100, it's going to tell me in this case what the percent ionization is going to be, which you'll see right here on the next page. And you'll see in this case, when I multiply by 1, it says, hey, based upon this thing right here, I get a value equal to 0.42%. That's the percent dissociated we have. There we go. If we look at this new problem, and when I say new, it's really not new. The only thing I did for this second problem is I just made that concentration a little bit smaller. But still, even if I make that concentration smaller, I'm going to still do the exact same sort of setup that I did in the last problem. I'm going to write my equilibrium, fill out my ice chart. Once again, that's my initial concentration sitting right there. Plug it in right here. 0, 0, minus x, plus x, plus x. 0.100 minus x, x, and I got x right here. I'm going to test it to see, once again, can I get rid of that minus x to prevent me from having to use a quadratic equation? And if you look at it, if I take, in this case, this value times 100, so now we're going with 0.1 times 100, 0.100 times 100, and I need it to be 0.100, which is the initial concentration. Oh, I'm sorry, that's not the Ka. The Ka is right there. 1.8 times 10 to the negative fifth. So that's going to end up giving me now, once again, when I multiply this times 100, the same value I had sitting right there before. 1.8 times 10 to the negative second in this case. And if I look at it, I can see that this is going to be smaller than this. So I get rid of that minus x again. Thank goodness, I don't have to go through the quadratic. So getting rid of that minus x, and then just going through and saying, hey, you know what? I know the initial concentration was 0.100 m of the HC3, well, H2, C2H3O2, divided by, so that's the initial concentration, divided by the concentration of what the hydronium cation is going to be, 1.3 times 10 to the negative third m. And that's of the H3O plus, times 100. Once again, once I plug this into the equation and multiply it, I get a value that's going to be equal to 1.3%. One thing to point out is that when it comes to percent ionization, or the degree in which the acid is going to dissociate, is only really useful if we start problems off with the same initial concentration. And let me kind of explain why this is going to be the case. If we have the same concentration, as a matter of fact, let's just do this analogy here. Say I was to walk into, once again, at 7-Eleven. I've got $10. I walk into 7-Eleven and I spend $5. I can say I have 50% dissociation with my cash in that case. So 50%, $10, once again, spent $5. I have another person, such as, once again, Mr. Chompin. He walks into 7-Eleven. He's got $10 as well, but he spends $7. Then we can say that he has a 70% dissociation. We can clearly say that Mr. Chompin absolutely spent more money than Mr. Harrelson in this case. That's fine, because we both started off with the exact same amount of money. But at the same time, if I walked into 7-Eleven and I spent, in this case, $5, 50% of my money again, and Jeff Bezos walks in and he spends $1 million. Well, if you look at the degree of dissociation, I spent 50% of my money is gone. But Jeff Bezos, because he is a billionaire, hasn't even touched a percent of his money. But overall, he spent more money than me. So if we think about it from that perspective, one of the things that you will notice here is that you technically have a lower percentage ionization. But at the same time, if I look at, once again, what I'm afraid of this thing right here, the hydronium cation. And what you'll notice is that even though you have a smaller percent dissociation, you've got a larger amount of the H3O plus in the water in comparison to this one that has a higher percentage, which is 1.3 to negative third. So if they're different concentrations, this thing doesn't really do anything for me. Percent ionization is really only going to be good if we're comparing two things that have the same identical concentration. So starting off with the exact same amount. And this slide right here, once again, it kind of says the exact same thing. Percent ionization is only useful if we're comparing two acids at the exact same initial concentrations. If we're not, then it's really not going to be that beneficial. And the analogy that I gave you here that I kind of went over with Mr. Chaffin, I also have the analogy sitting right here. But this one I kind of used Mr. Griggs. And in this case, Mr. Griggs, I said had $5. That's all his money that he has. All the money I have is $500 in this case. Once again, we both walk into the store. In this case, what do I get here? We both went to a vending machine. In this case, we bought $2. In this case, I bought $2 of water. And Mr. Griggs bought a Twinkie and also a Diet Pepsi, but he spent $2 as well. So we both spent $2. If we look at our percent dissociation, you'll notice that, hey, for Mr. Griggs, he dissociated from 40%, in this case, of his actual wealth. While me, I only had a 0.4 dissociation. Even though we spent the exact same amount, we get different percentages, and that is because we're starting with different initial amounts here. So once again, percent ionization or percent dissociation, only good for if you go in there and start with the same initial amount. All right, here we go. So this is a problem that we kind of looked at previously where, hey, they tell us that we got 0.2 molar solution of this weak acid, 2.5% of it. The acid dissociates, and they want us to find the Ka. So one of the things I could do is I could use our equation here. This simply says that, hey, the initial amount of the acid divided by the H3O plus. And then once again, I can substitute in, I can solve for X, where I know that X is going to be representative of the H3O plus concentration. And because I was able to figure that out, that means that when I go through my ICE table, I already know what X happens to be. That's the percent dissociation. So I just take that value, substitute in for X, and I can figure this thing out. And then once again, so long as I substitute in my X values, I can figure out what the K is going to be. So just one thing just to point out really quickly. You have choices here when it comes to this sort of problem. This is going to be given on the equation sheet, so you have it sitting there. If you want to kind of commit, and I can commit to memory, but realize on the equation sheet, I can use this to ultimately get to X, where X is going to be equal to my H3O plus concentration. That is fine. It works beautifully. But at the same time, we don't necessarily need this. We kind of looked at this sort of problem when we were looking at equilibrium problems earlier. And if you look at it, it tells me that 2.5% of this is actually dissociated. Which means that if I think about it, I'm just going to write down here my acid HA initial is equal to 0.200 molar here. And then the percent dissociation is 2.5%. What you could have done if you wanted to is you could have done like we've done earlier. If this represents the degree of dissociation, so 2.5% of this dissociates, well, that's really telling you what this X is right here anyways. So if I wanted to figure out what X was, I would just simply say, hey, the degree would be 0.200 m times, in this case, 0.025. And when I do that, I'm going to get the exact same, if you look at the math, it's the exact same math that I have sitting right here. 0.2 times the 2.5, but of course divided by 100, It's the exact same, which means I'm going to get 0.0050 m, which of course is going to be representative of my x in this case, because that shows me the degree of dissociation. So for me, I'm not committing that equation to memory. I'm not even thinking about the equation. I'm just realizing that once again, if it says any equilibrium problem, I don't care if it's a weak acid, a weak base, not even an acid base, just one of the problems we had previously. I'm always just thinking about when they tell me dissociation that they're referring to that thing. That's the degree at which it's going to dissociate here. All right, that's it for the weak acids. We're going to discuss really quickly now. It's just bases. Bases, it's going to run through really quickly because there's not much new here. You're going to attack these problems pretty much the exact same way you're attacking the acid problems. So here we go, bases. One of the things that we know is that when it comes to strong bases, these things are just based upon the solubility rules. And we said that earlier. So earlier in the lecture, one of the earlier videos, it makes mention of the fact that, hey, if we have a strong base, then we're just looking for a base that is soluble as an ionic compound, in this case, in water. And if you look at the solubility rules, it says, hey, hydroxides are normally insoluble, except for if they're attached to the alkali metals, ammonium, calcium, strontium, or barium. So these are some examples in this case of strong bases, things that can deliver the hydroxides in this case. And one of the things that we said earlier is if we have the concentration of a strong base, because it 100% dissociates, whatever its concentration is going to be the concentration of the hydroxide. And then we also looked earlier at these problems right here, where I gave you the concentration of a strong base, and we said, hey, if that's a strong base identified, here goes, once again, its concentration. I can use the Kw expression to figure out, in this case, what the H plus is, or I could take the negative log of this, got the POH. Subtract from 14, either way, I'm getting the exact same answer, 12.70. If we look at this problem here, oh, and let me go here. I forgot I had the second option up here. Option 1, option 2. Hey, go here, and once again, find the POH, subtract from 14, and you get the same value. Over here, if you look at this one, just be careful once again. If it has the ability of dropping off 2 hydroxides, then I know that I gotta multiply this concentration since there's for every one of these, there's twice the number of hydroxides, so I multiply it by 2. Take the negative log, I got the POH, subtract from 14, and I got the pH. So strong acids, nothing new here. We know how to deal with these things. What I wanna discuss is going to be our weak base. Now, when it comes to weak bases, remember what a base is. A base has to accept the hydrogen cation. That's what a base is going to do. So when we look at these bases, we're going to see something that kind of looks like this here. Where, hey, you know what? It'll even tell you the problem that, hey, ammonia happens to be a base. So because it's a base, what's going to end up happening is it's going to simply accept the hydrogen cations, because that's what bases do. They accept the hydrogen cation. And of course, if it accepts the hydrogen cation, what's going to be left of the water, because remember, water is really just kind of like this thing of the H plus and also hydroxides. If I take the H plus away, then I got the hydroxide that's going to be sitting out there. So in this example here, the H plus is coming over here to the nitrogen. It's going to deposit itself on there. I'm going to get NH4 plus, because it's now taking on the +1 charge. And then I got my hydroxide sitting right here. And keep in mind, and once again, on the AP, they're not going to just leave you out there. They're going to say, hey, ammonia is a base. Once you hear it's in a base, just say, okay, well, it's the one that's going to accept the H plus. Pretty straightforward. Now, when it comes to bases, instead of having Kas, we have the base dissociation constant, which is called the Kb. Nothing's changing. Products of reactants, everybody raises their coefficients, no solids, no liquids. And if you look at it, I would just literally substitute in my values here. If they ask me, which I'll probably end up doing, what is the pH of the solution? Well, I can get to the POH and then just ultimately get to the actual pH. Now, I want to explain how this thing can actually accept, in this case, the actual hydrogen cations. And one of the things that you're going to notice when it comes to these bases is that a base is going to end up having, in this case, lone pair of electrons. And the reason why we need lone pair of electrons is if you think about something, I'm going to go back to this problem right here. if we think about ammonia, what ammonia looks like, if I gotta just write its dot structure, it looks like this right here. So here we go. Then I got my lone pair of electrons sitting right there. Water, I got something that looks like this right here. I got H, we'll go with this here. X, 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 X. We'll go X, O, H, and X, O right here. So if we look at it, what's gonna happen in this actual equilibrium is this hydrogen right here is gonna come off. So it pops off. And because it lost this electron, it's like, hey, I'm out here as H plus in this case. But if you think about it, we know hydrogen wants a duet. It's like, I'm not happy. But if you look at it, what do I got sitting right there? Lone pair of electrons. Which means what it has the ability to do is to simply deposit itself right onto the lone pair of electrons. In this case, we get nothing more than a good old coordinate covalent bond, where I'll just put an X here. Hydrogen's gonna deposit itself right there. And then what do I have here? I get one additional electron that's with the water, and that's why now I got the hydroxide over here looking like the following. It's like, hey, I get one additional electron. So of course, don't forget Lewis dot structures. Anytime we got ions, we got to make sure we put the bracket around it and put. So I'm just showing you from a kind of like a molecular level what's going on. The hydrogen is always going to simply find lone pairs and plop itself right onto the lone pair. So one of the things you're going to notice is that bases are always going to have lone pairs for the hydrogen to dump itself. Look at water. Even if you look at water, I can see that water has the ability for a hydrogen to plop itself right onto that lone pair in this case. So we need some lone pair of electrons. Now, a lot of times when you're in a C basis, even in the homework assignment, you'll notice that quite a few of the bases are going to have nitrogens in them. Nitrogen-containing compounds have these lone pairs, which are just perfect to accept, in this case, that hydrogen from the actual water. So you'll notice here, there goes ammonia, lone pair. Here goes pyridine with a lone pair of electrons, lone pair of electrons, lone pair of electrons. It doesn't have to only be nitrogen. We just need lone pair of electrons for the hydrogen cation to plop itself on from the actual water in this case. All right, here we go. Second, just lost my place in the slides. My view is different from your view. We are right here. All right, there you go. All right, really quickly, we're gonna look at here. We're just gonna take a look at how to make sure that we can write the equilibriums for a base. Once again, your homework is gonna say, hey, ammonia is a weak base. And if we gotta write the equilibrium, just say, oh, you know what? It's gonna be the hydrogen cation acceptor, so H plus. Then you're just gonna go over here and say, okay, well, we got one more hydrogen, you're plus one. Plus, because that H plus is coming from the water, I get hydroxide kind of left over here, aqueous and aqueous. Even right here, codeine. If I look at codeine, codeine will interact with water. And it tells you that codeine is a base. So all I do here is, once again, take the hydrogen, I'm gonna bring it over here, and then you're just gonna write, in this case, I'll put hydrogen here. And I don't care if you wanna put it here and say it's C18, H22. Just make sure you add the hydrogen somewhere into this thing. I'm gonna go this route here. I like to put it in the front. H18, C18, H21, NO3, aqueous, plus we're gonna end up having now the hydroxide, OH minus aqueous. And that's it. As simple as that. So when you look at tonight's homework assignment, they're gonna say, hey, it's a base. And they ask you to kind of do this, and that's what it's gonna do. And the very first part is gonna ask you, hey, take this and show how it interacts with water to produce the actual hydroxide. All right, one last thing that we're gonna look at really quickly, it's gonna go really quickly. It's just how to deal with these sort of problems as far as, hey, figuring out what the pH is gonna be. And the reason why I can say this is gonna be really quickly is because there's nothing changing here. Only difference is, once again, we're now dealing with KBs because this thing happens to be a base. So if I look at ammonia, it says, hey, ammonia happens to be a base, here goes a Kb, and look at this, I even show you ammonia right there. It's just waiting for a hydrogen cation to come in here and kind of plop itself onto those lone pairs. So if I look at this, first thing I would probably do is go in here and write my equilibrium for this base. So I'm gonna go aqueous, I'm gonna go with H2O, liquid, and equilibrium. In this case, once again, the H plus or the base should accept the hydrogen cation. I get NH4 positive aqueous, plus I'm gonna end up getting hydroxide OH minus aqueous. Running through this problem, if they tell me that's the initial concentration, once again, I always told you, it's gonna sit at the initial. 15.0 molar here, 0, 0, minus X, plus X, plus X. I get 15.0 M minus X, plus X, plus X. And then the rest, I'm just gonna show you really quickly, because what I know is that if I get to the X here, I can get to the OH, find the POH, and ultimately get to what the pH is gonna be here. So if you look at it, first thing I got going on right here is the exact same thing in your notes. So I just showed you how I produced that grid here. One of the things that I know I probably should do is go ahead and let's test to see whether or not we can get rid of this actual X here. And we said that once again, if I can multiply 1.8 times 10 to the negative fifth, times 100. So take the Ka times 100, and so long as it's lower than the initial concentration of this base, I can get rid of the minus X, and when I do this, this is equal to, I just lost it, less than 15.0 molar. It passed the test, I'm getting rid of the X there. So if we look at it, that's exactly what I did. I was able to get rid of that minus X that we have sitting within the actual expression for Kb. No need to go through the quadratic at this moment now. X, once again, which is going to be equal to the OH minus concentration. I can go through and simply do the following. I can use the Ka, that's all I'm using here. I'm saying Ka is equal to the H3O plus concentration times the hydroxide concentration, where we say Kw is 1 times 10 to the negative 14. And that's all I did. I just solved this case for the H plus, took the negative log. But, maybe a quicker way is just to find the POH. Take the negative log of this, subtract from 14, and you get the same value sitting right here. All right, we are done in this case with our actual weak acids. This is another example. You can kind of take a look at the notes. It's the same sort of problem. But let me just point out really quickly. And I got some students that are going to come in a second. Give me 2 minutes and I'll be with you. All right, for this particular problem, we got codeine. I already told you that codeine happens to be a weak base. They tell me the initial concentration of the codeine is given right here. They tell me the pH is right here. They want me to figure the Kb. Shouldn't be a problem. So the first thing I'm going to do is I'm going to write the actual equilibrium. So for codeine, just like I showed you before, just take the H off of the water and deposit it onto the codeine. You got your hydroxide right here. I'm pretty much done here. Because if you look at it, all I'm going to do is I'm going to go ahead and fill in my ice grid. And when I go in and I fill in my ice grid, you're going to get something that looks like this. Initial concentration 0, 0, minus X plus X plus X, minus X of this, plus X, and I got my X here. If you remember in the previous problem, or in the earlier part of this problem, they told you what the pH of the actual solution is going to be. If I know the pH, then I can get to the pOH. And if I can get to the pOH, that means I can get to the OH minus concentration, which would be 10 to the negative and whatever the pOH is. Which means I know in this case what X is because it's going to be sitting right here. And then I can just go through once again, and that's kind of what I did right here. I just went up here and I said, hey, you know what? The pH happens to be, what did they give us? It says 9.95. So the pH is 4.05. And then after taking that, I figured out what the OH concentration was. There it goes, base 10 to the negative 4.05. Here goes my hydroxide concentration. Once again, once I get my hydroxide concentration, I realize that is my X. I have everything I need in order to figure out, in this case, what the Kb happens to be. So you're gonna have some problems just like this in tonight's homework assignment. This is where I'm gonna stop. You are gonna go to Veracross. On Veracross, there's gonna be a worksheet that says weak bases. 2026 worksheet. You will complete that worksheet and make sure you hand it in tomorrow. And I'll have a show me folder sitting there for you to actually hand it in. All right, this is where we're gonna stop and we are done for today.